DC or direct current motors are fairly ubiquitous in the world, especially when you're thinking about mechatronic systems. So hybrid car, for example, a lot of hybrid cars include DC, in this case, brushless motors. We're going to be talking about brushed motors. Toys, cell phone vibrators, they're just everywhere, honestly. And so it's a really good case study to dive deep and really look at a model for how these actuators are actually working. And so these are electromagnetic actuators, and we're specifically going to talk about the brushed variety of DC motor. And the electromagnetic portion of this, or the electrode portion of this, is going to be provided by this coil right here. So through this coil, I'm going to be running some current I, and obviously there might be many loops of this coil, but I'm just going to draw one for simplicity's sake. The magnetic part of this electromagnetic motor is set up by these permanent magnets here, and I have a north pole and a south pole for my magnets. And that will ultimately generate a magnetic field that we'll call the B field, moving from north to south. So I have B is my magnetic field that's created from those permanent magnets, and then I is the current in my windings. I have some other parts of this as well. So at the end of this coil, I have the commutator, and then attached to, or kind of up against that, are going to be my brushes. And that's why this is a brushed DC motor right here. So these orange things are the brushes. So those are basically providing some physical contact to the commutator as it's going to rotate around. So I don't have a fixed physical contact, but the brushes allow me to rotate that commutator while staying in electrical contact with it. And then applied to those brushes is going to be some supply voltage, and that's a DC voltage, to my motor. So that's ultimately what's providing the current through here. The permanent magnets are providing the magnetic field, and what's ultimately going to drive the motor are the interaction between those two things. So just some definitions here. These permanent magnets are forming my stator. That's the stationary part of my motor. And my coil that's rotating is going to be the rotor, or the rotating part of my motor. If I want to understand how those magnets in my current are going to interact in order to drive something around and provide some kind of torques and the like, I'm ultimately going to want to derive some law that defines that particular interaction. And so I'm going to start getting there with the Lorentz force law. And the Lorentz force law from physics is giving me a force based on a current applied over a length with a magnetic field. So I, in this case, is my coil current again. L is the length of the coil, and there's also some direction associated with that. And B is my magnetic field. So if I look at this graphically, such that I have my coil, so I'm looking end on with my coil, so my current is effectively going into here, right? That's represented by the X, it's going into the page, and then the point represents current coming out of the page here, right? So with this cross product here, I'm effectively using my right-hand rule. My magnetic field, once again, is going from north to south here. And so I have an I going into the page crossed with that B. And so I have a force pulling down on this side of the coil right here. And similarly, I have my current coming toward me crossed with that magnetic field, and so I'll be getting a force upward on this side of the coil. So I have two forces, right? They're going in opposite directions due to the current going in opposite directions on each side of this coil here. So I can simplify this cross product so that my force is going to be ILB sine theta. And the way this is designed, where I have these permanent magnets here and this coil always rotating like this, those current directions, at least in this part of the coil, are always going to be 90 degrees with respect to that magnetic field. So sine theta, where theta is 90 degrees, is always going to give me 1. So I can think of my force as my current, my length of my coil, and the magnetic field that I'm generating with those permanent magnets. For rotating DC motor, ultimately what I'm interested in is torque. So if I'm rotating, in this case, around some center point right here, it's obviously going to depend on the length between these parts of the coil that are generating my forces. And I'm ultimately going to get a torque, right, that's some I times some length constant on one part of the coil. So coil 1 times length coil 2 times that B, and I can simplify this further to T is KT times I. And this is what I'm going to define as my motor law. So this KT term here is basically taking into account these parameters, which are based on the geometry and the magnets in my motor. So these are my motor parameters, and KT is what I'm going to call my torque constant for a motor, right? So that's defined for each motor based on some parameters of the coil and the magnets in that motor. And that's going to have units of Newton meter per amp. T here is my torque, and I is the motor current. But this equation right here ends up being very important in defining the torque output that we would get from our motor. So this is what we call the motor law, and it's based on the torque constant, so general parameters of the motor, as well as the current that we push into that motor. That's going to define the torque that we get out. I'm trying to understand the speed output that I would get from this brushed DC motor. I'm going to go back to Faraday's law. And Faraday told us that rotating coil through a magnetic field will ultimately generate a voltage that tries to oppose that rotation. And this is the general principle that's used for big electrical generators. They're basically DC motors used in reverse. And we call this voltage the back EMF, or VEMF, where EMF stands for electromotive force. So this will also be strictly proportional. So this back EMF that I get, or VEMF, is going to have some constant of proportionality times my speed. So we call this constant KE, and that is going to be our speed constant. Omega is the rotating speed of the motor, and VEMF is our back EMF voltage. So speed, of course, can be given in units RPM, revolutions per minute, or radian per second. So radian per second are obviously the SI units. RPM are fairly common though. The speed constant, also as a consequence of that, is going to have units of V per RPM or V radian per second. Obviously this one is our SI, but volts per RPM is probably something that you'd more commonly see in a data sheet. So this equation right here, that's our generator law. So I've ended up with these two constants, the torque constant and the speed constant, so KT and KE. And I think it's really important to think about how these two things are related, because ultimately they're related back to the parameters and the design of my DC motor. So I'm going to make a really big assumption in analyzing this, and my assumption is that there's going to be no loss in my DC motor. And that basically means no resistive heating, it means no friction in any kind of bearings or in those brushes. There's no loss. It's a pretty bad assumption, but at least allows us to understand how these torque and speed constants are related. So if that's the case, then I'm going to have my power output equal to my power input, effectively efficiency of 1. So my power output is going to be my torque times my speed. My power input I can think of as the EMF voltage times the current. So torque obviously was KT times I, then times omega. VEMF was KE times speed times I. And what I see here, the I's and the omegas cancel, and I end up with KT is equal to KE. Obviously, we typically write these in different units, so we really need to just be thinking about how we convert the units to make sense here. So KT, when given in Newton meter per amp, is going to equal 9.55 times 10 to the minus 3 times KE, if KE is given in volts per kilo RPM. Another common unit for the torque constant would be inch ounces per amp. In this case, we're going to multiply by 1.354 when KE is given in volts per kilo RPM. And I will emphasize for both of these that we're looking at kilo RPM. And so this gives us some way of going back and forth between torque constant and speed constant, but ultimately they're all tied back to the same motor parameters, right? Which is why they're equal in this case when there's no loss in my system. Using those two laws, I can come up with a fairly basic model for my motor. And that model is going to include a resistor, an inductor, and that VEMF voltage source in series. So the resistance in this case is going to be my coil resistance. And that's of course given in ohms. L is going to be my coil inductance, given in henries. VEMF, from the generator law, we know is going to be KE times omega. And if I hook this up in a circuit with some supply voltage to my DC motor here, that supply voltage will be sourcing some kind of current. The bit in blue here is my DC motor model. And I have a couple more variables here. Vs is just my supply voltage to the DC motor. And I is obviously the coil current. And so I can do Kirchhoff's voltage law on this circuit. So if I go around here, I'm going to get my supply voltage is equal to the voltage drop across the resistor, the voltage drop across the inductor, and that EMF voltage right there. So these are my plus minus, VL, VR across these respectively. All right, let's look at VL real quick because I haven't talked about this inductor yet. So if I'm looking at the voltage across an inductor, that voltage is going to be defined by the inductance and the derivative of the current going through this. So if I make an assumption around this operating at steady state, I can assume that that voltage drop is 0. Right? My current's not changing because I'm at steady state, so VL is 0 in this case. Right, so in this case, VR is just going to be my current times the resistance. VL is 0. My back EMF voltage I know is KE times omega, where omega is my speed. I also know from my motor law that this current is going to be equal to torque over that torque constant, so T over KT. So in this case, I'm going to get a final equation describing this whole circuit, basically a supply voltage hooked up to my DC motor, where Vs is going to be my torque over my torque constant times the resistance, the coil resistance, plus Ke times omega. So this basic motor model is ultimately going to give me some understanding of how I can trade off, for example, torque and speed, or how my motor coefficients or my motor constants contribute to torque and speed with a given voltage supply and coil resistance in a motor.